Hello students, let us talk today about BSc Semester 3rd Maths Unit 1 Convergence of Sequences, in which we are discussing today Cauchy's general principle of convergence of sequence. In this, one theorem is expressed here. The necessary and sufficient condition for the convergence of sequence Sn n is equal to 1 to infinity is that for each positive number epsilon there is a positive integer m such that in mod Sn plus p minus Sn, here it is in lower script, okay, S in lower script n plus p minus S in lower script n in mod is less than epsilon for all n is greater than or equal to m and for all p is greater than 0. This p should be greater than 0. So if we subtract the previous term from the next term, then it will be always, and then take its mod, then it will be always less than epsilon, where it is this epsilon is positive number. A sequence of real numbers, this theorem can also be expressed as a sequence of real numbers is convergent if and only if it is Cauchy's sequence. See, once again, a sequence of real numbers is convergent. It will be convergent only if and only if it is Cauchy sequence. If it is not Cauchy sequence, in that condition, a sequence of real number is not convergent. So, try to understand this statement. A sequence of real numbers is convergent if and only if it is a Cauchy sequence. This theorem can be asked in this manner also, in this manner also. The necessary and sufficient condition for the convergence of sequence Sn n is equal to 1 to infinity is that for each positive number epsilon, there is a positive integer m such that mod of Sn plus p minus Sn less than epsilon for all n is greater than or equal to m and for all p is greater than 0. This can also be asked in examination in this form. State and prove Cauchy's general principle of convergence. It is very important theorem for the examination point of view and for your basics also related to semester 3, and it was asked more than 3-4 times in Vikram University also. So proof is expressed. The condition is necessary. So in this, let the sequence Sn from n is equal to 1 to infinity be convergent and let L be its limit. Suppose what we have considered, that this sequence from n is equal to 1 to infinity, Sn from n is equal to 1 to infinity be convergent, and let convergent means what? Its finite limit will exist there. So it will be convergent and let L be its limit. What limit we have considered? L be its limit. Thus for a given epsilon is greater than 0, this is another part, remember. This is the part for condition is sufficient. So, thus for a given epsilon is greater than 0, there exists m is element of n, an initial number, such that Sn minus L mod of Sn minus L is less than epsilon by 2. What we have considered? Sn minus L, because L we have considered as a limit as it is a convergent sequence. So Sn minus L mod or mod of Sn minus L is less than epsilon by 2 for all n is greater than or equal to m. If p is greater than 0, then n plus p is greater than n, of course. If p is greater than 0, then of course n plus p is greater than n, which is greater than or equal to m. So mod of Sn plus p minus L, what we have considered, p is greater than 0. That's why we are taking here Sn plus p minus L. This n plus p is in lower script. So Sn plus p minus L, mod of this complete is less than epsilon by 2 for all n is greater than or equal to m and p is greater than 0. Now, from this, what we can conclude that Sn plus p minus Sn can be expressed as Sn plus p minus L plus L. What we have done in modulus, we have added limit L and subtracted limit L. Here in this, Sn plus p minus Sn can be written as mod of Sn plus p minus L plus L minus Sn mod closed and less than or equal to Sn plus p minus L mod that I have expressed in my previous theorem also, that mod of A plus B will be always less than or equal to mod of A plus mod of B. This is one condition that you remember. So in place of A, what is there? Sn plus P minus L, and in place of B, L minus Sn. So these two are separated, that's why less than or equal to sign will be there. Here it is equal to sign, but here it will be less than equal to sign. Then it will be less than epsilon by 2, as it was epsilon by 2, and this is also epsilon by 2. So epsilon by 2 plus epsilon by 2. It is less than epsilon by 2 plus epsilon by 2. So 2 will be taken as LCM. So epsilon plus epsilon, that is 2 epsilon upon 2, that will be equal to epsilon. So what we have concluded is that Sn plus P minus Sn is less than epsilon for all n, and P is greater than 0. For all n or m, we can say, and P is greater than 0. The condition is sufficient. See, the condition is sufficient. Try to understand this now. This we have applied in one more theorem, which was explained in previous part or previous lecture, we can say. The condition is sufficient, in which what we have to do to establish the convergence of sequence under the given conditions. To establish the convergence of sequence under the given conditions, we first of all show that, what we have to show first of all, that sequence is bounded. What we have to show, that sequence is bounded. Here we have considered it bounded, and then written this. Now we have to show that sequence is bounded and converges to a limit, to a particular limit, or converges to a particular limit. Now from the given condition, for epsilon is equal to 1, if we take epsilon is equal to 1, there exists, this is the sign of there exists a positive integer m0 such that Sn plus P minus Sn, see here it is, Sn plus P minus Sn is less than epsilon. We have proved here, but in place of epsilon we are taking 1, that's why Sn plus P minus Sn is less than 1 for all n is greater than or equal to m0 and P is greater than 0. In particular, for n is equal to m0, now if we consider n is equal to m0, we have what we have now. In place of n, we have to write Sn0 plus in place of n. In lower script, we have to write now m0 plus p. Sn0 plus p. m0 plus p is in lower script minus Sn0, where m0 is in lower script. Mod of this complete is less than epsilon for all p is greater than 0. Now what we can conclude, that Sn0 minus n minus 1, sorry, Sn0 minus 1 means, I want to explain it directly to you, that this Sn0 plus p will be in between Sn0 minus 1 and Sn0 plus 1. Here this minus 1 and plus 1 is in main script, not in lower script. So Sn0 minus this Sn0 plus p is in between Sn0 minus 1 and Sn0 plus 1 for all p is greater than 0. So let G is equal to minima of this complete sequence S1, S2 and so on. Sn0 minus 1 in lower script, m0 minus 1, comma, Sn0 in main script minus 1. It is minimum, this G. And this capital G, here only one change is there, that is Sn0 plus 1. So what we can conclude by this, that this Sn is in between G and small g and capital G. So G is less than or equal to Sn is less than or equal to capital G for all n is element of natural number. Hence the sequence is bounded. Here it is bounded. Bounded means what? Try to understand the term bounded. Bounded means having its lower limit also and having its upper limit also. In between lower and upper limit it will be existing. Then in that case we can say that this sequence is bounded. So hence the sequence is bounded because here it is lower limit and this one is upper limit. So hence the sequence is bounded. Therefore by Bolzano-Weierstrass theorem, the range set Sn is such that n is element of capital N has a limit point, say small n. We now show that limit n tends to infinity Sn is equal to L. Now what we have to show, that limit n tends to infinity, Sn is equal to L. This we have to show, and we have to proceed with this now further. Now see, up to here it is limit n tends to infinity, Sn is equal to L. We now show. So for this, now from the given condition, for epsilon is greater than 0, there exists m is element of n such that there exists m is element of n, means m is element of any natural number. For epsilon is greater than 0, Sn plus p minus Sn is less than epsilon by 3. Mod of Sn plus p minus Sn is less than epsilon by 3 for all n is greater than or equal to m and p is greater than 0. Now, in particular, for n is equal to m, suppose in particular we are taking n is equal to m in this place. In place of n we are substituting m. Then it will be mod of Sn plus p minus Sn. In place of n we have written m. So it will be Sm plus p minus Sn, and mod of this complete is less than epsilon by 3 for all p is greater than 0. This is considered as our first equation. Now, since L is limit point, there exists an integer m1 greater than m. As L is the limit point, there exists an integer m1 which is greater than m. Means one more consideration we have taken which is greater than m. That consideration is m1. m1 we are considering greater than m. So such that Sm minus L is less than epsilon by 3. Here Sm minus L is less, mod of Sm minus L is less than epsilon by 3. It is our second condition, because m1 we have considered greater than m, so m is less. So we may write here Sm minus L, mod of Sm minus L is less than epsilon by 3, and this is considered our second equation. Now, also since m1 is greater than m, therefore from first what we can get, if we solve this, so it will be Sm1 minus Sm, from first, Sm1 minus Sm, according to this one, this first, because this p is greater than 0, so if m1 is greater than m, means it is greater than this m1 is greater than m now, and here p is greater than 0, that's why Sm plus p minus Sm is written. So by this first equation we can conclude this also, that Sm minus 1 minus Sm, mod of this complete is also less than epsilon by 3. So now we are having three equations, first, second and third. Now Sm plus p minus L can be written as, see here, Sm plus p minus Sm plus Sm minus Sm1 plus Sm1 minus L. Means what we have done, we have added and subtracted Sm, we have added and subtracted Sm1 also. So minus Sm is written first, then plus Sm, and then minus Sm1, and then plus Sm1, and Sm plus p and minus L was written as it is. Therefore, if we take mod sign here, then we have to take the mod of this also. So this mod of this complete is equal to mod of this complete. But if we separate these three terms with mod sign, then there will be less than or equal to sign, that I have told you, that mod of a plus b plus c is always less than or equal to mod of a plus mod of b plus mod of c. So less than or equal to sign is due to this reason. So by this we have written here less than or equal to Sm plus p minus Sm in mod, and then plus Sm minus Sm1, and then plus Sm1 minus Sm. Means line wise we have written in a consecutive manner. So this part Sm plus p minus Sm, see it is less than epsilon by 3, and Sm minus Sm1, Sm1 minus Sm or Sm minus Sm1, both are one and the same thing because modular sign is there. So this can also be considered as epsilon by 3, and Sm minus L, this is also less than epsilon by 3, so it was also considered less than epsilon by 3. So less than epsilon by 3 plus epsilon by 3 plus epsilon by 3. So here 3 is taken as LCM. So epsilon plus epsilon plus epsilon, that is 3 epsilon by 3. So 3 will be answered. It is equal to epsilon only. So it was also, we have done one more time. For 2 we have taken 2 limits here. And by 2 we have taken. But in this case we are dividing it by 3 here. So it will be 3 epsilon by 3. So epsilon is the result. So Sn minus L, mod of Sn minus L is less than epsilon. This, it implies that, what it implies? That Sn minus L is less than epsilon. See what we have done. Sn minus L only we have taken in our previous part. See, limit n tends to infinity, Sn is equal to L. This was, we have to show. So Sn minus L, it implies that Sn minus L, mod of Sn minus L is less than epsilon for all n is greater than or equal to m. Hence, the sequence Sn from n is equal to 1 to infinity converges to L. What we have proved that it converges to L only. This mod of Sn minus L is less than epsilon. This only we need to prove, and this was only the sufficient condition. So both necessary and sufficient conditions are proved for this theorem. And thanks a lot for watching our channel, and please do like it, subscribe it and share it as much as possible.